Hello, and good morning, good evening, good night, wherever you are in the world. Welcome to this webinar in the TOPIQ webinar series. My name is Christian Schürmann, and I would like to introduce to you my dear colleague, who is also called Christian Göb, and he will give us a webinar about the crystalline sponge method.
Thank you, Christian, for your introduction. This webinar is being recorded. The recording and the processed data will be made available to you. You will receive an email with download instructions in the aftermath of this webinar, or you can go straight to the past webinars webpage. If at any point during the webinar you have a question, please feel free to submit them by clicking the Q&A button on the bottom of your Zoom screen. My co-host Christian will collect all questions and we will answer them by the end of the webinar. Before we start, I would like to ask all of our users to join the Rigaku X-ray forum. Here you can get updates on Rigaku activities, download Crystalline Pro, and follow interesting discussions on all fields of crystallography. If you're already a member of the forum, I would like to encourage you to subscribe to your specific fields of interest so you get an email alert when something new comes up. The way you characterize a substance depends on its availability, chemical nature, and information that you like to obtain. For solids, single crystal diffraction is the method of choice to obtaining the positions of atoms, their bond distances and angles, or their interactions in the packing of the crystal. If large enough crystals are not available, that means smaller than 1 micrometer in all directions, you could still perform a powder diffraction experiment and obtain lattice parameters. Structure solution is possible in case the system is not too complicated with careful Rietveld refinement. The powder XRD you see here was collected using an XRLab Synergy S single crystal diffractometer. A recording of the corresponding webinar, Micro XRD with a single crystal diffractometer, is available on our webpage. See the link on the bottom of the presentation. If your substance is difficult to crystallize because it is a liquid at room temperature, or if only a few milligrams are available, then spectroscopic methods like NMR or infrared spectroscopy can be used to derive connectivity of atoms or certain chemical groups. With multidimensional NMR, it is even possible to derive the size of a molecule, the multiplicity, and the coupling constants tell you about the chemical environment of the studied atom nucleus. The information gathered by these methods is very valuable in synthetic chemistry, but you will not obtain an absolute structure from those experiments. Is even fewer substance available? The only option left for a long time was to perform high resolution mass spectrometry. From the shape, mass, and charge of the signals, you could at least calculate the chemical composition. Fragmentation patterns would show the dissociation of chemical groups. Growing a single crystal from such little amounts of substance is impossible. So how can you obtain a crystal structure from a substance that does not crystallize? You can use a metal organic framework and fill its pores with the analyte of your interest. Such porous crystals used for this method are called crystal sponges. In a simplified glance, you soak the pores of those crystals with an analyte like a kitchen sponge soaks up the water. This method was introduced by Professor Makoto Fujita from the University of Tokyo in 2013. As little as 80 nanograms of substance are needed for this method. If you have more available, then that's better, of course. The soaking process is typically executed from a single crystal in conical shaped vials, as you see on the photo. Let's take a look from which substances those sponges are made of. The classic Fujita sponge consists of a TPT ligand, that means a tris-pyridyl triazine ligand, which is cross-linked by zinc halide moieties. The most commonly used zinc halides in the synthesis are zinc chloride and zinc iodide. Zinc iodide has the advantage of a stronger diffraction compared to zinc chloride. On the other hand, zinc chloride has fewer absorption issues in comparison to zinc iodide, which makes it easier to refine the gas molecules soaked into your framework pores. Depending on the metal salt, different solvent systems need to be applied for a successful synthesis of the desired host framework. Gas molecules cannot be soaked into the sponge pores because the polar solvents methanol and nitrobenzene that were used in the synthesis typically occupy the pores. They themselves are very good binding polar gas molecules. Although some compounds can be soaked into the crystal sponge pores from chloroform directly, typically the solvent is exchanged to cyclohexane or a short chain aliphatic hydrocarbon like N-hexane or N-pentane that has only weak interactions with the host framework and does not bind into the pores strongly. The whole sponge method is very well described and documented in the IUCR journal publication from 2016. If you wish to read yourself into this topic deeply, then I recommend to begin with this article first. The crystal sponge itself is a porous metal organic framework with voids along the crystallographic 101 direction. The pore channels exhibit a diameter of 5 by 8 angstrom and serve as the crystalline backbone to analyze compounds that are otherwise inaccessible to diffraction methods due to their low availability, because they are liquids at room temperature or gaseous. Because of these properties, the method is used in pharmaceutical industry to determine the crystal structure of metabolites, or in food production to determine the flavor compounds of hops and beer, for instance. I want to give you an example that was published just 2 weeks ago in the journal Drug Metabolism and Disposition in a collaboration between the Helmholtz Institute for Pharmaceutical Research in Saarland and the company Merck in Darmstadt, Germany. Understanding the metabolism of new drug candidates is important during drug discovery and development, as circulating metabolites may contribute to efficacy or cause safety issues. In this study, phase 1 and phase 2 metabolites of gemfibrozil, a drug used in treatment of abnormal blood lipid levels, was digested using rat and human liver microsomes that oxidize the active pharmaceutical compound. In this process, different metabolites M were detected by using HPLC-MS or UPLC-MS. The mass spectra of metabolite M1 and M2 show the same signal at 265 M/Z. That means they are equal in weight, but different in retention time. Clearly, the oxidation of gemfibrozil must have been occurred at different atom sites. Because only very little substance amounts are used in these experiments, a crystal sponge can help to determine the proper crystal structure. The electron density maps revealed the constitution of the soaked up metabolites. M1 is oxidized at the C3 group and M2 is oxidized at the phenyl ring. A result that would have remained unclear with such small substance quantities. On this slide, the gas soaking of compounds from the gas phase is demonstrated. The crystal sponge is exposed to fumes of Japanese wasabi. After a few days, allyl isothiocyanate can be detected inside of the crystal sponge pores, together with the solvent of the crystal sponge that the crystal sponge was suspended in. In this case, transdicalene was used as a solvent because it has a high boiling point and it dissolves and attracts the allyl isothiocyanate very well. So how do you prepare those sponge crystals? The crystallization is quite easy and straightforward. The difficult part is the gas soaking. You simply layer the TPT and the zinc halide solution on top of each other in a test tube. The test tubes are equipped with a screw cap, which becomes very handy since those test tubes can also be used for the latter solvent exchange process. Here you can see a rack of different crystallization attempts. Depending on how careful you layer the solutions on top of each other, the produced crystals will be many small or very few big ones, as on the right. Like for the most single crystal deflection experiments, the crystals should roughly exhibit a size of 100 to 150 micrometers. The crystallization is usually completed after 2 to 3 days. Then the crystals are combined in one test tube and the solvent mixture is gradually exchanged to 100% of weakly binding solvents like cyclohexane. Single sponge crystals are selected under solvent and transferred to conical shaped microvials, together with the addition of 1 microgram of analyte. You want to pick just the very perfect crystals with well-developed faces, without cracks or any attachment to them. The vial is then pierced with a short cannula and the soaking and solvent evaporation process is performed at 50 degrees Celsius usually. What do I mean with picking perfect single crystals? On the left, you can see single sponge, you can see crystal sponge, single crystals. On the right, you can see twin sponge crystals. The twin domains are usually oriented 180 degrees to each other, since the A and C axis of these compounds are almost of the same length. By naked eye, it can be difficult to tell them apart. You really want to check the crystals from all directions. On the left-hand side, you mainly see block-shaped and rod-shaped crystals. The block-shaped crystals typically crack less upon gas soaking, since the analytes do not have to penetrate the crystal in comparison to the rod-shaped crystals as deeply. After selection of the right crystal comes the soaking step. To the single crystal in the vial comes the analyte. Finding the right soaking conditions will decide on success or failure of the method, and there is no universal soaking protocol that could be applied. In fact, the soaking conditions must be screened and optimized for every substance individually. This is crucial for the success of your experiment. The parameters that need to be optimized are the choice of the co-solvent for the analyte. Typically, chlorinated solvents like chloroform, dichloromethane, dichloroethane, or DME are used. The temperature and evaporation rate have a big influence on the alignment of the molecules in the cavity. Absorbed gas molecules should be thermally equilibrated throughout the crystal sponge. That means there should not be a gradient of disordered molecules, nor should the excess gas molecule be fixed on interstitial positions in the crystal lattice. This can also be adjusted by the analyte concentration. The crystal quality is crucial too, as I already pointed out. A good starting point for soaking is to add 1 microgram of analyte solution to 1 crystal sponge, submerged in 50 microliters of cyclohexane. The soaking and evaporation can be performed at 50 degrees Celsius for 1 to 2 days. Why should a gas molecule bind inside of the crystal cavity? There is a few effects that we need to consider. One is the hydrophobic effect. The cavity of the sponge pores is typically very hydrophobic and therefore favorable to bind organic molecules. If the organic molecule has a certain shape, it will fit very perfectly into the pores and bind strongly. The gas molecule can interact with the host framework by aromatic stacking or CH-pi interactions. The zinc halide moieties are good hydrogen bond acceptors. The host framework itself is a donor for hydrogen bonds. So what is an ideal data collection? The crystals should not be too big, as I pointed out. They should have roughly a size of 100 to 150 micrometers. You want to collect your data at 100 Kelvin, and you definitely want to use kappa K alpha radiation. You are aiming for an I/sigma greater than 10 for the high angle data, and you want to have a redundancy of at least 3. The system best suited for such data collection is a Synergy R in combination with a large area detector like the Hypix ARC 150. With this setup, the best soaking conditions can be screened at a glance, and the crystal sponge method will be successful. Using a seal tube system, it is also possible to collect data on these. The data collection typically take much longer time, and you will not be able to screen all of your different soaking experiments in one day. Absorption correction of the data set is very crucial, especially for the zinc iodide-based sponges. We recommend to collect the high angle data first, since these MOF crystals degrade during the measurement due to radiation. Because they degrade, it is advisable to do a B-factor refinement in the UPSPAC when scaling your data. In Chrysalis Pro, you can save a crystal sponge pre-experiment, in which you can decide on the exposure time factors and the sorting of the runs to begin with at the high angle theta first. When you are going to the strategy calculation, on the right-hand side, you also have the option to sort your runs according to the absolute theta value and collect the high angle data first. I just want to show you a structure solution and refinement of an easy, that means very well soaked structure solution of a crystal sponge together with the refinement. Before you can see the gas molecule, the host framework needs to be fully refined anisotropically, including the disorders of the zinc halide moieties. After this, the gas molecules should at least be partially visible. It is generally a good idea to soak a few crystals and get your hands onto this technique before you soak your very precious analytes. Gas molecules often show a disorder to some extent. It could be a superposition of two analyte molecules or a mix of analyte and solvent. The sum command might come in handy if more than two molecules should be treated. Sometimes the assignment of carbon, nitrogen, and oxygen can be difficult. This depends on the quality of the data set, the scaling and absorption correction. Some chemical understanding for the binding motifs and molecular interactions, like in small molecule crystallography, are needed as well to assign the atom sites properly. If the analyte is not visible at all, or only small site occupancy factors are observed, you need to adjust the soaking conditions. Superlattice reflections or satellite reflections arise from improper soaked, not thermally equilibrated crystals. Constraints and restraints are very useful in refinement of crystalline sponges and sometimes unavoidable to obtain a good structure model for your analyte. And for the end, I want to come back to the example that I showed to you earlier. I just want to show you how constraints and restraints can be applied to get your structure model. As you can clearly see, the electron density map indicates the position of the oxygen atom, and there is no doubt which is the metabolite 1 and which is the metabolite 2 in these examples. And with that, I would like to thank you very much for listening. I hope you enjoyed this webinar. We welcome your questions. If you have any feedback or suggestions on future webinar topics, we are also very happy to hear them. Thank you very much.
Thank you very much, Christian. So I'm going quickly to switch on my camera. So there are a couple of questions already, and I would like to read them to you. So the first question is there any limit in the volume or the size of the guest molecule that can be included in such pores?
Well, the pores have a defined size, which is 5 by 8 angstroms. Of course, the framework is a little flexible. It can soak up probably analyte molecules that are a little bigger than that, but you should be below that. That's the upper limit that you can soak.
So then there are two similar questions. The one is that asking whether you can use zinc bromide, I think for the preparation of crystalline sponges instead.
Mm-hmm. Okay, so as I said, typically zinc chloride and zinc iodide are used. Zinc iodide is the sponge that diffracts more strongly, but has the problems of absorption correction. Mm-hmm. Zinc chloride, on the other hand, does diffract weaker and has less problems in absorption correction. Zinc bromide is an intermediate, and typically this is not employed. There are not as many publications using the zinc bromide sponge as there are of zinc chloride and iodide.
And the next question is, are other crystalline sponges available? So apart from changing the anion, can you also change other things in your sponge?
Mm-hmm. Oh, yes, sure. So this topic or this webinar was about the classic Fujita sponges. Of course, there's also other metal organic frameworks that can be soaked with analyte molecules. Quite recently, there was also a Nature publication about a co-crystallization approach, where you can co-crystallize your analyte molecules to get a crystal with some other molecules. I will put maybe a few links to that when we upload the video, and then you can read into those if you like.
So next question, for larger guest molecules, would longer soaking be required?
So I assume larger means not larger than the pores. So you have to adjust the soaking conditions for every analyte that you soak. I think for me, it is too difficult to give you any prediction on the soaking time and the proper soaking conditions. You have to find that really out for each compound individually.
Mm-hmm. Then the next question is, can you please elaborate on the soaking procedure at 50 degrees Celsius? Doesn't this evaporate the solvent over 2 to 3 days, and does that help the soaking into the pore?
Mm-hmm. So when you soak up a molecule into the sponge pores, you always have an equilibrium where the analyte molecule wants to be dissolved in the solvent, or it wants to go into the pores. If you decrease the amount of solvent, you are shifting this equilibrium more to the crystal sponge side. So in the end, slow solvent evaporation over the course of a few days will help you on soaking.
And on that same topic, which is the best way to optimize the soaking conditions?
That's a very tough question. I have to say.
Probably you can do PhD thesis about that.
Yeah, probably. Well, so what you really want to do, because the data collections on crystal sponges using sealed tubes is quite long, the best way to do it is to screen in one batch different analyte concentrations maybe screen in the same attempt 1 or 2 temperatures, and then do many data collections, and then you get a rough idea which screw you have to turn and adjust for the best soaking condition.
Okay, then another question. If we use the synergy S, I expect that it will take longer time than the synergy R. Is the if the crystal will survive? No, will the crystal survive during that measurement? I don't have a rotating anode source, and therefore.
Yes, for sure. So the data set of this caffeine molecule that I presented to you was collected on a synergy S of this molecule. So there's no doubts. You can also collect it with sealed tubes, but it will take much longer time.
Mm-hmm. Okay. So is the geometry of the guest molecule different in the crystalline, if it is crystallized in a sponge compared to if it is crystallized by itself?
Yeah, it should be. Well, if you imagine you have a flexible group attached to your molecule, the conformation that you obtain from the crystal structure is depending on packing effects if you have a flexible molecule. And therefore, I would expect a substance crystallized in a sponge can adopt a different conformation than crystallized by itself or as an adduct with solvent.
Mm-hmm. So do you have any experience of different levels of purity to analyze solution that have been tried? So soaking conditions with impurities may happen?
Mm-hmm. Yeah, in fact, so the crystal sponge will soak up everything basically that is very hydrophobic. Yeah. So if you are using much plastic equipment, for instance, which has plasticizers in it, you might soak up the plasticizer before you soak up your analyte material. So when you do crystal sponge soaking, you are aiming for very pure compounds that you soak up, and you want to use only glassware. And yeah, you just want to make all the conditions perfect to soak up your analyte molecule, and you could not soak up one specific molecule from a mixture of many, probably.
Okay, good. I think that's, oh, there's more coming in. Are there restrictions on the guest molecule besides the volume? Can it maybe react with the sponge? Or
yeah, yes, for sure. So when you synthesize the crystal sponge, you employ a solvent mixture of chloroform and methanol. If you have a too high methanol concentration, or if you have water inside of this solvent mixture, then probably you will not form the sponge network itself. So if your analyte molecule has many carboxylic acid moieties, for instance, or something, this could be harmful for the frame network, and maybe they cannot be soaked.
all right. So thanks again, Christian.
Thank you very much.
Thank you all for listening and attending. We hope to see you in another webinar. And until then, goodbye.
Goodbye, everybody. Have a nice day.